Definition of pumping lemma. What is the pumping lemma? The term pumping lemma is made up of two words, that is pumping or lemma. Pumping means word refers to generate any input by pushing any kind of string in an input string for repeatedly. Lemma means refers to that immediately theorem in a proof. There are two type of pumping lemmas for languages, that is regular language and context-free language. Let's discuss about the pumping lemma for the regular language. The theorem is for the pumping lemma regular language. If L is a regular language, then L has pumping length P. Here we will take the pumping length P such that any string S where the length of S is greater than equal to P. Whatever the length string will be taken from this length, that is greater than the pumping length, may be divided into three parts, that is S equal to X, Y, Z, such that follow the condition, these three conditions. What are the three conditions here? X, Y to the power I, Z belongs to L for every I greater than equal to 0. Then second is length of Y is less than 0, and third is length of X, Y is less than equal to P. Let's discuss more about that length. In simple, if string Y is pumped for insert any number of time, the resultant still must be regular language. That means remaining in L. Pumping lemma is used for proof that irregularity of the language. That means whatever the language we are taken, we have to prove that one, the language is irregular. This is not a regular language. It means that is regular language is a regular, not a regular language. It always satisfies the pumping lemma if least one string made up of pumping, not a language, then L is a not regular language. We use the contradiction method to prove that language is a not regular. Next, steps for the regular language. Step 1. Assume that suppose we'll take a regular language L. Step 2. It has a pumping length P. Step 3. All string longer than the P. That means length of S greater than equal to P. Next step for step 4. Now find the string S and such that S is greater than S. Length of S is greater than P. Next step 5. Divide the S, whatever string is taken from this language, will divide three parts, that is X, Y and Z. Next, in step 6, so that X to the power I, Z not belong to L for some I. Then in 7th step, then the considered S can be divided into X, Y, Z. Here we have to put three cases. That means we will take the whatever the string is given, we will divide it into three parts. That is, if Y part is comes from the only one symbol, that is A, number of A's, and in second case, Y should be in symbol B, and next in third part is that Y should be A and B, taking symbol A and B. So that 8 steps, so that none of the above strings satisfy the three pumping lemma conditions simultaneously. Next step, S cannot be pumped, that is equal to condition. Then next step, we will discuss taking this pumping lemma with an example. For example, using pumping lemma, proving that language L, the language is L equal to A to the power b and uh, a to the power n and b to the power n. That means equal number of a followed the equal number of b is not a regular language. This language should not be a regular language. We are taking this language, then solution will be follow the steps. Whatever the steps we are discussed before, we will put in this example and discuss. Assume the language. First we have to, whatever the language we are taken, first we will assume that is a regular language and take a pumping length p, and let's string as a to the power p and b to the power p. After that we'll take the value of p. Next divide the s into, take the value of p equal to 7. I am taking here p's value is 7. So this is a to the power 7 and b to the power 7. That means here 7 number of b and 7 number of a. 7 number of a followed the 7 number of b. Therefore s equal to here 7 number of a's and 7 number of b's. So that here s is greater than equal to s, length of s is greater than equal to p, length of p. Next case we'll take, for this we get the string and we'll put the 3 cases. First case, why we divided this 3 strings in 3 parts, that is x, y, z. Whatever string we will get, we'll divided the strings are 3 parts, x and y. Then we'll take the first case. What is the first case here? Y consists of string having letter only one a symbol. That means whatever the x, y, z is divided, y part will be comes only a symbols. Take only one a symbol. Next, like this. So I am taking here 7. I take b, length of b is 7 and divided the strings like this. I am taking y part only a symbol and x as 2 s and other symbols including a, that is z. This one case 1. Then case 2. Y consists of string having letter only b, means b symbol. Here I take all the a's and b's and y are, I am taking 4 y symbols and z as 1 b symbol. Then third case, y consists of string with letter a and b. That means we will take the both a and b symbols as in y. So I take 5 y's, a's and ab, bb, aa and bb as y and other part, rest of symbols as z. Let's discuss other taking these symbols. So we have to prove that language is not a regular. For this we will take this part, that is x, y to the power z not belongs to L. That means this whatever symbol we are divided, that should not be belong to regular. For this I take the value equal to I. Suppose I am taking I value equal to 2. So x to the power I, x, y to the power I, z equal to x to the y to the power 2 and z. So that in first case I am taking all the symbol in a, that is, so that 4, I am taking 4s here. Here, so that in this a should be, if I to the power 2, I equal to 2, then that a should be double. That means here we will get 8 number of a. Here 8 number of a's. Now and rest of symbols are remain same. So now number of a is 11 and number of b is 7. So here clearly shows that this string is not following the regular language, original regular language, that is a to the power n and b to the power n. That means that is not following equal number of a follows by the equal number of b. So that is this language is not a regular language. This string is not belongs to this regular language. Next, case 2. I am taking y as only one symbol b. So that we will put this same formula x y to the power I and z. So that we will now y is I is 2. So y is b is become to 4 number of b's. So now the number of b is here 4 and number of b are 4 and so including all the number of b, its b is 11 and a is 7. So that it's also not following the original language, regular language. So this is not belong to regular language, not lies on our language. Next, case 3. Same x to the power x y to the power 2 z. So that in this third case we are taking two symbols a and b. So that we increasing to the power y to the power 2. So ab is repeatedly, but it's showing clearly that this portion of language, the string is not following totally the regular language. So that this is not considered as a regular language. Therefore, the language a to the power n and b to the power n, that is not a regular language. So this is the related video for the regular language with example. Using pumping lemma, prove that language a is a language that is that follows the language is like this: a to the power n and b to the power n. For some n is greater than equal to 0 is not a regular language. So if a is a regular language, then a has the pumping length p such that any string s where s length of string is greater than equal to p. I am taking here p as 7, p equal to 7. Though whatever the length will take after the pumping, that pumping length will be greater than the length of string will be greater than the pumping length. Suppose I am taking here s and I am dividing that s into 3 parts, that is x, y, z, such that they are follow these 3 conditions for proving that language is regular or not. But the 3 conditions are there, that is x, y to the power I and z belong to a. A is here the language whatever we are taken for every I is greater than equal to 0. Then second condition is this: length of y means whatever the string are divided into 3 parts, y length of y is less than 0, greater than 0. Then third condition is that length of xy is less than equal to p, pumping length. Including these 2 lengths, including that length of xy, p should not be greater than them. To prove the regular language not a regular language using pumping lemma, following the steps. The steps are assumed that a is a regular language. It has second step is it has to be pumping length, say let's take p. All string longer than the p can be pumping, so that length of s greater than equal to p. And third is now find the string s in such that is same s length of s is greater than equal to p. Now divide the whatever the putting that pumping length in S string, whatever the string is occurred, that will be divided into three parts, that is x, y, z, so that x to the power I z not belong to L, A, language A, for some I. So we'll put that I's value from 0 to 1. After that, we'll check that string should not be belong to that regular language, whatever the language we are taking. Then consider all ways that S can be divided into X and Y. Let's take an example. Here I am taking this example, that is language. Suppose I am taking a language A to the power n and B to the power n. So I'll prove this, take this language. This is not a regular language. So that I'm taking P as 7 and I'll put that S, taking from this language a string, that is A to the power P and B to the power P. So I'm taking here P as 7. So there is 7 number of A's and 7 number of B's. Now this string should be divided into three parts, that is X, Y and Z. Whatever number of A and B will divide as X and Y. So I am taking here number of I'll taking these strings in different three cases, that is in first case string should be should be in only one symbol, that is A, and in third case, second case, B should be in the only B parts, and in third case, A should be in from the only two symbols, that is A and B. So that I am taking these symbols like this, A and B. I am taking here X as 2 A's and 4 A's as Y and 1 A and rest of B's as Z. This is first case. So now the A's are, all A's are 11 number of A's and 7 number of B's. So this is total clear that this this string is not following the original language, that is A to the power n and B to the power n. So this string is not comes under the regular language. So then second condition is all B's are Y comes into all B's. So here I am taking 4 number of B's as Y and 1 B as Z and all rest of A and 2 B's as X. So that here putting that Y to the power 2, so B's are now 7 number of B's and 11 number of A's. So that this is clear, so that this string is not following the original language. In third case is that Y is in the A and B part. That means Y should contain all the A and B parts, both A and B. So that A and B, I am taking 2 A's and 2 B's and X as 5 A's and other B's as Z. So it's clearly, if I put this condition, that is X to the power, first condition, that is X, Y to the power I, Z, and Y to the power I's value is 2. So that it's showing totally not following the pattern of the original language. So this is the first taking these cases. After that, putting this first condition, that is x equal x y to the power I and z, that is i's value is here 2. I am taking 2 here. So here if I'll put the I, then y value will be double here. So this is 11 number, including 2 value, 2 i's, it is 11 number of a and 7 number of b's. So 11 is not equal to 7. In our first language, that is number of a is followed by number of b's. So here this is 7 number of a and followed by 11 number of a's followed by the 7 number of b's. So this first condition also not satisfied, and second condition also not satisfied, because I am taking y as all b parts. So if b is increased, that means 4 number of a's. So 4 number is, so including all b's, that is 11 number of b's and 7 number of a's. 7 is not equal to b, so this is not following the original language. Next is third part. Y comes under the both a and b symbol. So if we'll increase this y to the power 2, then ab and ab. So this is totally clearly showing that this is not following the pattern. Whatever language we are taken, a to the power b and a to the power n and b to the power n. So this is clear, this language is not a regular language. Okay, next we'll start about the pumping lemma for the context-free grammar. Context-free language generate the context-free languages, that is the set of context-free language is same as the set of language accepted by the push down automata. The set of regular language is subset of context-free language. Pumping lemma for the context-free language said that any context-free language L, if it is possible to find the two subset that can be pumped any number of time, and still it will be contain in any language, and pump the second and fourth substring. Here in pumping lemma, will pump the second and fourth string of the term of the string with the conditions. Then the language is not a, will prove language not a context-free language. Take this next. So let's implement of the pumping lemma for the context-free language. Suppose language L is context-free, then there will be existing any string p is greater than equal to 1, and also called the pumping length, such that every string s in context-free language L width has been length of p more than written as. Here suppose s is a length and that is divided into 5 parts. In regular language we are dividing the language that is in 3 parts, that is x, y, z, but for this pumping lemma, whatever the string will taken, that will be divided into 5 parts, that is u, v, w, x, y. So that we'll taking this string will follow the 3 properties, that is u v to the power n, w x to the power n, and y belongs to L for every n greater than 0. That means whatever the string is given, whatever the value will be for n, that should be follow the regular language, original regular language. And second condition is that length of xb is greater than equal to 1, and third condition is vwx, length of vwx less than equal to P. Means length of this is the x length of x w x v w x less than equal to P pumping length. Next, what is step to apply the pumping lemma. So take a language, assume that L is a context free language. The pumping length will be n. All string longer than the length n can be pumped. So string is taken here w and length should be greater than equal to n, means greater than to the pumping length. Now we have to find the string w in L such that w greater than equal to n. We'll divide the string w into the part u, v, x, y, z. Now so that u, v, x, y, z, u to the power u, v to the power k and x, y to the power k, z not belong to L for some constant k. That means whatever the pumping length we'll get, we have to prove that that language should not be belongs to that should not be a context free language. Then we have to consist of all way to find w can be divided into this part u, v, x, y, z. So that none of these satisfy three pumping lemma, then condition that string will be not a pumping lemma. A string w cannot be pumped or that contradiction. So this is the condition. Suppose the language is L context free, then there will be existing any language string integer p, that is p is pumping lemma and greater than equal to 1. That in regular language pumping length always greater than equal to 0. So we'll take here p is greater than equal to 0. Now we'll divide this length as u, v, w, x, y. Then after that, whatever the string is given, we'll prove that through that conditions. Now we'll discuss about the pumping lemma for the context-free language. Context-free language generate the context-free languages. The set of all context-free languages in the same set of languages accepted by the push-down automata. That means context-free language is always accepted by the push-down automata. The set of regular language is a subset of context-free language. The pumping lemma for context-free language states that for any context-free language, L is possible to find two substrings that can be pumped any number of times and still be in the same language. That means whatever the string will be taken from this context-free language, whatever the time will be pumped, that remains same. Otherwise, it will be not considered as context-free language. We break it in string into that strings into 5 parts for any language L, and pumping the second and fourth substrings. In regular language, we'll divide the substring x, y, z, but in context-free language, we'll divide the strings in 5 parts, that is x, y, u, v, x, y, like this. So from this string, we'll take the second and fourth part of the substring. If any string does not satisfy the condition, then the language is not a context-free language. Implement of pumping lemma for the context-free language. Suppose the language L is context-free, then there will be the existing any integer p greater than 1, also called pumping strength, such that it has length that every string S is the context-free language L which has the length of p, or more can be written as. So that string should be divided into u, v, w, x, y. That is, here string is divided into 5 parts. This substrings are following these 3 properties. That is, first one is u v to the power n w x to the power y belong to L for every n greater than equal to 0. Next condition is that length of u, v and x greater than equal to 1. And third is length of u, v, w, x less than or equal to p, pumping length. This is the topic I discussed about the pumping lemma. Thank you.